Thanks, Doug. Thanks for having me here. It's always nice to come to this workshop every year. So today, like Doug said, I'm going to do something a little different. Hopefully something that's a little fun and invokes some curiosity, maybe answer some questions, maybe create some questions, because today this talk's not about like my research or my graduate students' research or anything like that. It's just kind of like getting back to the fundamentals, the basics of what makes ice crystals grow the way that they do in clouds. How can we relate that to what happens in a snowpack, things that we're all interested in. And then how can we relate that to beer, something that we also probably all interested in, right? So let's just dive right in here, and I'll try and put this all together for you as we go. So who's seen this very famous figure before, the Ukichiro Nikaya diagram for snowflake morphology? So this is a great overview of how you get different crystal habits that form in clouds as a function of temperature on the x-axis and basically humidity on the y-axis. And so you can see how you get at warmer temperatures, you can go from plates to columns, and then from columns back to plates, and then from plates you can have plates or columns. And what that is all a function of is not just the temperature but also the humidity. All right, so I really like this figure, but I also think it can be a little bit misleading because what we're really talking about here is not like relative humidity like we usually think about with the weather. We're talking about supersaturation. So how far beyond 100% relative humidity do you need to be to get ice crystal growth in a cloud? All right, so this supersaturation is at 0. That's kind of like 100% relative humidity at 0. And then we're going up above that, becoming supersaturated. There's more water vapor in the air than it can really hold. And of course, that's a function of temperature too. So supersaturation of water vapor in air relative to ice is what this really is, higher humidity. It's above 100%. And then another interesting line of demarcation on this Nikaya diagram is this curve that cuts through the middle. That's a supersaturation curve of supercooled water, as in supercooled little cloud droplets, water droplets in clouds. And where you get this really interesting demarcation between something like, walk in front of the light, something like plate growth versus like dendritic growth, something more complex. And so in general, the takeaway from this is that temperature controls the habit formation of plates or columns, and then more supersaturation gives you more complex shapes to your snowflake development. So what is supersaturation? You might already know this, but I like to describe this and I like to think in simple terms. So basically, if you think about a glass of water, or here I have a flask of water that's capped at the top, you will reach a point of equilibrium where there's enough water vapor in this airspace above such that the exchange of water vapor and water molecules within the filled part of the water is exactly the same. So these arrows are the same magnitude. There's always something happening, dynamically, at the surface of a liquid. And so we've got water molecules leaving the surface of the water, and we have water molecules that are in the vapor phase entering the water just from the energetics of temperature. So that's equilibrium. Saturated, that's like the 100% relative humidity. You could take the same flask of water and put it under vacuum, and then you can guess what's going to happen. Under vacuum, you're going to evaporate all the water, and eventually you'd see the water disappear in this flask. You could have the subsaturated environment. This is the classic environment where you leave a glass of water on your nightstand for like a week and you go back and there's no water in it because it was in a subsaturated environment. Like we live, our relative humidities around Montana are generally low. And so we get some condensation from the vapor phase to the liquid phase, but we get mostly evaporation. Eventually we lose all of our water. And then we get to the supersaturated case. How do we get to supersaturated? Basically, you take your flask of water, you leave the cap on it, and you put it on a hot plate, right? Just like boiling water. So you're raising the temperature, you're evaporating away a lot of the water molecules that were down here in the liquid phase, but at the same time, they're trapped. They can't go anywhere. So you're essentially putting more water vapor molecules into that space than it wants to have at that temperature. So what happens? You can see on the walls of the flask here, condensation. Like it wants to just have that phase change, given something to nucleate on. So this is the idea behind the supersaturation that is in the Nikaya diagram, and kind of a simple way to understand it. Now let's apply it to clouds. So how does a cloud form? A cloud is not just a body of water vapor, it's a body of liquid water droplets. And so essentially we need to have a high concentration of water vapor such that we get supersaturated or highly concentrated. Then, just like the water condenses on the glass of the flask, it wants to condense onto anything that's in the cloud that can act as a nucleator, like dust particles or aerosols or things like that. And then once it has a little bit of water that's condensed, then it's easy for more water to sort of latch onto that from the water vapor that's in the air. And when we have that happen, over a large volume or area, we get a cloud, right? It's composed of all these little liquid water droplets. It's not quite the whole story though, because what we haven't talked about is what's the source of the water vapor. So the air naturally just has some amount of water vapor in it. I'm sure you guys know that, but if you have a source of water vapor, then you can have higher concentrations. And so obviously liquid water makes a good source for water vapor. And you can see this process play out where you might have water vapor evaporating off a body of water. It goes up as it rises, that the water vapor cools. Then you get, as it cools, the right conditions for supersaturation. And then you get the condensation on little dust particles, smoke particles, whatever. And then you get the cloud that forms. And then you can have rainfall or snowfall from the particles that form after that. This is the idea behind something that I'm sure everyone has been hearing a lot about this year, atmospheric river events. So atmospheric river events are essentially corridors of concentrated water vapor that are being shot, for us, towards the continental United States, usually from a more equatorial area in the Pacific. And so you're getting a bunch of water vapor showing up at this one spot, and when it hits the mountains, of course, it gets lifted, and as it lifts, it cools, and as it cools, it condenses, and you get the potential for precipitation in the form of rain or snow, depending on temperature and elevation. So I know what you're thinking now. Where's the beer part? So what does this have to do with beer? All right, so now that we've kind of got some basics behind cloud science and formation, think about beer is pressurized and supersaturated with carbon dioxide, with CO2, right? That's what makes it bubbly. So it's pressurized and supersaturated with CO2, but when it's sealed, when the cap is on the top, it's in equilibrium because the gas or the air in that part of the neck right above the liquid is sealed at the top, and so it's in equilibrium with the pressure of the CO2 in the beer. So it's like having that water in the flask with the top on it, right? It's all in equilibrium. But what happens when you pop the top? You hear the little psst, right? You let that pressure out, and the temperature in the neck can actually drop by almost 40 degrees instantly from the expansion of the gas. This is like ideal gas law stuff. So you get this rapid gas expansion, you get this rapid cooling, so you basically have, in the neck of the bottle, there's CO2 gas, but there's also a lot of water vapor because beer is mostly water. And so that remaining air then becomes supersaturated instantly as soon as you pop the top on the bottle of beer, and it forms a cloud. So believe it or not, I'm sure you all have experience with this. Crack open a bottle of cold beer and look in the top, and there's going to be a cloud in there. And that's kind of what I did for this video. I really wanted to do this live, but I figured I didn't want to make you jealous being the only one drinking beer up here. So I did this at home last night. So I popped the top, there's the cloud, neat little trick. Shine a laser pointer in on the side so you can see the cloud. And now if you blow on it just a little bit, you can see the cloud inside there sort of swirling around. So it's that mixture of condensed. So those are tiny, tiny liquid water droplets in there, making that little cloud in the bottle. And then you drink it and it goes away. So this is a fun experiment to try at home. However, I'm going to warn you, it does not work with non-alcoholic beers. So I tried that too. And it didn't go so well. So that's what I learned from that experiment was I got to go get a real beer for this, otherwise this is not gonna work. All right, so now we've got the cloud, right? We've got the supersaturated conditions for the water droplets in the cloud. Now, how do the water drops freeze? How do we actually get snowflakes and ice crystals to form? So there are basically 4 different ways that you can nucleate a ice particle from water vapor or from liquid water. One is called the homogeneous method or homogeneous nucleation, where you actually have enough water vapor that it comes together and it's cool enough that it just forms a little ice embryo and it grows from that point on. This really only happens in like the highest parts of the atmosphere where the cirrus clouds are, so you go straight from vapor to solid. Usually what we see is immersion and contact, a form of heterogeneous nucleation, where basically if you have like a little nucleator, like something that can be either immersed in the liquid water droplet, shown here, or something that can come into contact with the liquid water droplet, shown here, then you can get freezing of that water droplet at a much warmer temperature. So this is like more mid-troposphere kind of heights where this happens, more typical of our precipitation events that we're most interested in. And then once you have an ice nucleus that's formed, you can get water vapor molecules that deposit onto that and grow the crystal. I'll come back to that in a minute. But there's a really great video here from Michigan Tech from about 10 years ago that shows this process of immersion and contact nucleation. So little liquid water droplets put on a slide, they cool the box, and then they wait for it to nucleate. And so you can see one nucleated from the side via contact nucleation and one nucleated from the middle via immersion nucleation. I'll come back and play that one more time. Another observation that you can make about this, which is really cool, is that you see that hexagonal shape that grows out from the middle of the water droplet. I mean, that is the crystal structure of ice. And so if that's how these liquid water droplets are freezing in clouds, then you sort of get the intuition that, well, snowflakes are probably also, single crystals, hexagonal particles, which they are. All right, so how about that? So nucleation is an important part. Contact nucleation is we can also observe in beer. So given that beer is supersaturated with this carbon dioxide, once the bottle is opened, the CO2 nucleates bubbles via contact nucleation. So it's supersaturated, just like the water droplets in the cloud. All they need is something to latch onto, and they nucleate bubbles. So for this, I used, again, nothing better than the banquet beer Coors. It also works really well because Colorado beer is a little dirtier than Montana beer in general. It's for you. So you see all the bubbles, right? So that's the supersaturated environment of the beer in the glass, and the bubbles are nucleating on just little asperities around there in the glass. Fun little home experiment, drop little salt granules in there, and the salt granules act as little nucleators, right? So you get CO2 air bubbles that are nucleating on those, and you get lots and lots and lots and lots of bubbles. That'll work with anything you drop in there. It'll work with sand. Doesn't have to be salt. Anything that'll ideally sink to the bottom and not just get stuck floating on the top will work for that. So in many ways, beer is just an inverse cloud. It's like if you took a cloud and pulled it inside out, right? Because instead of water droplets nucleating in air, we have carbon dioxide bubbles nucleating in the liquid. It's really just the inverse. So, I mean, that's one of the morals of my talk today was if you want to understand snowflakes, go drink beer, and you'll be getting pretty close. So how about, how do the ice crystals grow? So once you have that little ice nuclei that's formed, it continues to grow at the expense of the other liquid water droplets around it. So you basically have all these little water vapor molecules evaporating away from the liquid droplets and coming over to the snow particle or the ice particle, and it gets bigger and bigger and bigger. This is a real famous picture that you might have seen, where these are all little water droplets around this snowflake, and you can see how this little gap around it is like where all that water vapor is moving from the liquid to the solid and growing the snowflake. Okay, next. So we've seen a couple times that snowflakes have, or these ice crystals have 6 sides. And that's based on the hexagonal crystal structure of how the H2O molecules come together and bond. And we're familiar that we have like a basal face or a prism face, or what you might think of as like a C-axis and an A-axis. But do snowflakes have to have 6 sides? So the answer to that is yes. It's because of that underlying molecular structure. And so once you have this ice particle that forms into its little hexagon from all the molecules coming together, it then can start to grow little arms off of it, because these corners are sticking like further out into the surrounding water vapor. And so they start to attach there first. And it's like a positive feedback loop where it just keeps happening over and over again. Oh, I'm not ready for that yet. That keeps happening over and over again until you get the long arms. And I've got a good video to show for that in a minute. Here's a question for you though. Is it possible to have snowflakes with a different number of sides than 6? How many? Like when they break apart, yeah, all right. So the answer to this question, this is one of the things I really want everyone to remember if you don't remember anything else, is that snowflakes can only have 6 sides. Sometimes 12, but that's like 2 snowflakes that like joined in the middle and like grew separately. And sometimes it looks like 3, but really it's just like 3 sides of the hexagon are really small. So really just 6. So I hate to break the news to you, but if you were making paper snowflakes as a kid or with your kids recently, if you had 4 sides or 8 sides, it's not actually a snowflake. So you really got to be careful how you fold the paper. It's like kind of an art to get 6-sided snowflakes. Or if you spend a lot of money on Etsy for this 5-sided snowflake thingamajig, then I'm sorry about that too. Not a real snowflake. So snowflakes have to have 6 sides. It's not snowflake. And you'll see these everywhere. Just go walk around Main Street right now, and anything they're selling with a snowflake on it is probably not 6-sided. All right, so why all the variation in snowflakes that we see? So as a snowflake grows, it's floating through different thermodynamic conditions within the cloud. So this picture is from a multi-angle snowflake camera down at University of Utah some time ago that captured like all the different snowflakes that can fall basically during one storm. So you see a little bit of everything. You get some dendrites, you get some columns, you get some graupel, you get some aggregates, you get some like really rimed dendrites. You can see a little bit of everything. And the reason for that, coming back to the Nikaya diagram, is that as the snowflake is forming and growing in the cloud, it's not just sitting in a static location where everything thermodynamically is exactly the same. It's like taking its own little path down through the cloud. And as it does that, it's going through places in the cloud that might have different temperatures or different supersaturations, and it just responds. The kinetics of the growth just respond to that, kind of just like you see here on the diagram. So that's kind of the reason behind why 2 snowflakes really can't be the same, because it's impossible for them to travel the same path through the same conditions. Great example of that from one of my heroes, Ken Lebrecht. He's doing this in the laboratory. So these are not models. These are actual images from a laboratory experiment of ice crystals growing, where he has controls on temperature and supersaturation. And these are all little liquid water droplets around the snowflake there that you can see. And so he can literally sit there with the knobs and be like, oh, I want to have plates. No, I want like arms. No, I want plates. No, I want arms. And kind of make designer snowflakes. Super cool. And again, you can kind of see that Bergeron process of the liquid water droplets giving the water vapor to the snowflake as it grows. Another good example, and this kind of comes back to like some oddities, what you often will see if you go outside and collect snowflakes during a storm, is sometimes they grow kind of funky. They're not always perfectly symmetric like this. So here's 2 that started to grow at the exact same time. But now as they get closer together, they're competing with each other for the available water vapor. And so they're growing somewhat symmetrically, where they're not close to each other, but right in the middle there, they're kind of stunted. And so you end up with what looks like a 5-sided snowflake, but it's not a 5-sided snowflake. And you still see the hexagon, obviously, there in the middle. So another good example of how you get some different types of snowflakes from the same process. All right, just about done. Where else do we see these physics at play? You know, the Nakai diagram, the idea of supersaturation, condensation, deposition, growth. We also see that in the snowpack. The exact same like thermodynamics and physics are at play with the growth of depth hoar. As one example, depth hoar grows from temperature gradients. We all know that, large temperature gradients. And so you can get the hexagonal shape as one outcome of that. You can also get this kind of classic square shape as well. And that's a function of it not being in a symmetric environment of water vapor, but water vapor moving from like bottom to the top and growing these different, slightly different crystal habits from what we might usually see in clouds. But it's still water vapor showing up at a surface, that surface becoming supersaturated, and then the water vapor molecules depositing. And then surface hoar is another one where on those cold, clear nights, you're getting radiational cooling from the surface of the snow. That cooling right at the surface is creating a supersaturated layer of water vapor because of the drop in temperature. And then you get deposition onto the surface of the snow via the same sort of process. But now we're talking about water vapor depositing, you know, kind of down onto the surface of the nucleator, which in this case is ice. And I've got some pretty SEM pictures here from one of my graduate students, Evan, who's been working on this a little bit in the lab as well. So I'll just finish with a shout out here to kind of my two heroes in the field that have helped me along the way of thinking through this just through their books, basically, and their papers and whatnot. Ken Lebrecht at Caltech and Craig Bourne at Penn State, who wrote this awesome book, Clouds in a Glass of Beer, Simple Experiments in Atmospheric Physics. I highly encourage you to get a copy. It's a great bedtime reading, and it kind of gives you just general insights into the environment around us in terms of what's happening with the science. So in summary, if you want to learn more about snowflakes, go have a beer. Thank you.
Questions? I got one.
Yeah.
Is there a correlation between how much beer you drink and how many arms there are in a snowflake?
I'm pretty sure it's an exponential correlation of some sort there. Number of arms by how much volume of beer you consume, yes. Yeah, in the back.
So what temperature forms the perfect dendrite? Is it like 16 degrees or something like that? And why would that be the...
So we can just come back to this. So the question was, what temperature forms the perfect dendrite? I guess it depends on how you define perfect.
I think Alpha Snowflake, maybe Grom can answer.
So, I mean, really, you can just look at these ranges of temperature where you get dendrites. So like between 0 and like -3 or 4 C, or between -10 and -20 C, you can get this dendritic growth. If you're in the middle there, you get the columns. And so really, I've found that this kind of holds true. Like, I've been taking snowflake pictures with my daughter lately, got her like a little microscope and everything. This is really easy, another thing you can do at home, it's super fun. But generally, if the temperature's outside, you know, relatively speaking, it's really the cloud temperature that matters, but you know, on the right kind of day, the temperature outside, if it's in this like -15 range, be like, this is a dendrite day, you know, or it's a little bit harder to say that on the warmer temp days because things get really rimey pretty easily, but I think between this, I think like -15, if I just had to throw a number out, is like a good day for dendrites. You can always look at your sleeve and verify that.
Okay.
Yeah.
This is just anecdotal, and maybe I'm off base, but I've seen twinning in surface hoar and in depth hoar. Never seen it in snowflakes. Do you have any insight to that?
It happens in snowflakes too. So the question is about twinning. It's kind of like if you ever zipped your zipper in like the wrong spot and it like zips together anyways, but you know it's not, it's kind of off. Well, the way the crystal structures come together can be like that too. Where instead of making like just the perfect bonds between the molecules that it should have, it'll be like, I'm going to be off a little bit, but I still got like sort of close to the right bonding motif, and they can bond like that too. So that's called twinning when that happens in crystalline materials. And basically then you have not a single crystal, but a bicrystal that forms, because the crystallographic orientation will be in two different directions. I've got a great book that I can show you that will show that from some atmospheric particles that formed of twins.
Thank you.
All right, thank you.